we have the transistor, the gate potential is unknown, right. What are we going to do? We are going to measure the current in the source, which is ID again, compare it with, now I am not going to rewrite all the simple stuff that we have been doing so far. Now we should be in a position to maybe draw the circuits directly. ID is fighting, is you are comparing ID with IRF. So, what should I do? Where is IRF going to happen? In the source, okay. And we look at monitor that potential. If that potential, and we compare it with a, let us call this Vx, okay. We compare, if Vx is going up, what does it mean? This means that ID is greater than IRF, correct, which then implies it means that VGS is, it means that VGS is too large, which means Vg is too much, therefore, you must reduce Vg. So, if Vx goes up, summarize, if Vx goes up, Vg must go down, if Vx goes down, Vg must go up. So, what will you do? You therefore compare Vx to a constant, all right, and if Vx goes up, Vg must go down, and so on. So, what comment can we make? It is a voltage controlled voltage source. What must be the gain of this voltage controlled voltage source? Infinite. And so what must be the signs of the op amp? Source must be negative. Okay. So, in steady state, when obviously the negative feedback loop is stabilized, what comment can you make about Vx? What is the voltage Vx? That will be equal to V reference. What comment can you make about Vg? Yeah, how will you find out? From ID, how will you find Vg? From ID we can find VGS. Once you know VGS, Vg is nothing but Vref, Vref plus VGS. Is this clear, folks? Okay. And so that basically is yet another way of stabilizing the bias current of the transistor. Let me draw it a little nicer. And again, if you have not seen this circuit before, there is nothing to get, nothing to panic. All right. So, this is again. So, let us go through the exercise. So, let us say we did not know the signs of the op amp. What are we going to do? We assume some arbitrary signs. So, let us assume that this is positive, this is negative. You break the loop somewhere, go, you yank that voltage up. If I yank the voltage up at the gate, what happens to the source? Increase, goes up or down? Goes up. Why? Yeah. So, well, ID is greater than Iref, and therefore, this node potential will tend to go up. If that goes up through the op amp, what happens to the output of the op amp? Also goes up. So, this is positive feedback. All right. So, therefore, we therefore conclude that the signs we have chosen are wrong, and therefore, this correct signs must be this. Okay. So, this is our bias stabilization loop. Now, what are we going to do? We need to make a common source amplifier, yet another one. Okay. So, now again let us go through the, now you should be able to tell me what I should do to make this a common source amplifier. What should I do? Okay. So, basically we add the infinite capacitor here. Okay. And okay. So, again there is multiple ways of doing that. You can put an inductor there, or put the load resistor right there, or if you do not like that, you can put couple it with a capacitor, right, the usual thing at the load. Okay, fine. What else? We need to, again we need to break the negative feedback loop. So, how will you break the negative feedback loop? Yeah. So, you for example, you put an infinite inductor there, all right, okay, and so that will break. And what comment can we make? Are we done, or we still need something else to be done? The infinite capacitor, the source. So, the negative feedback loop only exists for DC bias. It is completely out of the picture for incremental signals, and this is our good old common source amplifier all over again. Does that make sense? Okay. And for each of these amplifiers, I mean, you can now go and figure out what the swing limits are, etc., right. Is the same old. You find the total potential at the gate, the total potential at the drain, the total potential at the source. Then there will be one condition for the transistor entering the edge of the triode region. There will be another condition that will push the transistor into cutoff, and you basically go, the minimum of those two amplitudes is basically what the maximum input swing you can tolerate will be. Is that clear, folks? So, so so this basically covers all the 4 ways of, with this we have covered all the 4 fundamental ways of stabilizing the bias current of the of the transistor, right. Once you stabilize the bias current in the transistor is ready for action, right, and therefore we basically can realize the properties of the transistor, namely the GM will be very well governed by the bias current in the transistor, which will not vary now even if the threshold voltage changes or the supply voltage changes. Okay. And in principle, therefore, I mean, and by the way, a common source amplifier is a transistor biased in saturation. In principle, is just simply an incremental voltage controlled current source with some transconductance GM. And in principle, is there any limit to the amount of transconductance we can get? Yeah, I mean, you have a transistor, right? What is the, I mean, and the GM, as you know, is square root of 2 mu n C ox W by L times I. So, in principle, is there any limit to the amount of transconductance you can get from a transistor? No, no, that is why I said in principle. But they are not fundamental limitations in principle. See, there is a difference between a limit in principle and a limit in practice, correct? All right. So, in principle, that the GM of the transistor can be anything, because you can go on pumping more and more current into the transistor. So, there is definitely so there is therefore there is no limit. On the other hand, in practice there is going to be some limit, like as pointed out before, right. I mean, you can't go on, I mean, of course, eventually you will burn the transistor and so on. So, in reality there is a limit, but in principle there is no limit. That is what I want you to be cognizant of. And the common source amplifier, therefore, is an amplifier which uses the transistor as in principle, you can get a very large gain using a common source amplifier, because in principle that GM can be very large, and therefore GMRL, the magnitude of the gain that you can get is very large. So, this finishes the basic common source amplifier, right. And remember what all, I mean, when you learnt your basic circuit theory, what are all the circuit elements that you saw, that you played with? The resistor, the capacitor, the inductor, and the 4 controlled sources, right. The voltage controlled voltage source, the voltage controlled current source, the current controlled voltage source, and the current controlled current source. If you are able to realize these 4 controlled sources, you can realize an arbitrary transfer function, right. From input to output, it can be current, voltage, current, whatever. Okay. And if when you have a controlled source, you can realize transfer functions with complex poles, correct. I mean, if you only want if you only want poles on the negative real axis, just RL or RC is good enough, and anyway in practice using inductors is problematic. But the moment you have controlled sources, then a whole lot of things become possible. So, the next thing that we will take a look at is how to make controlled sources, the 4 controlled sources that we have learnt in basic circuit theory, namely the voltage controlled voltage source, the voltage controlled current source, the current controlled voltage source, and the current controlled current source. We would like to build them using transistors, and we also would like to make sure that the so called controlling parameters of these the properties of these sources, namely, if you say I have a voltage controlled voltage source, what does it mean? What is the input impedance? of an ideal voltage controlled voltage source? Infinity. What is the output impedance? 0. And therefore, if we say I have a voltage controlled voltage source, the only parameter that you need to justify, that you need to specify is the gain between VO and Vi, correct? Similarly, if you have a current controlled voltage source, what is the only parameter that you need to specify? Current controlled voltage source, the trans resistance, because we know that the input impedance of a current controlled voltage source is, what is the input impedance of a current controlled voltage source? 0. What is the output impedance? The answers are only either 0 or infinity. It's a current controlled voltage source. What is the output resistance? Sure. Why? Why is it 0?
So if we change, means if it is a voltage source, then if we change any resistance, voltage will not get affected.
We change what resistance?
Output resistance. Load resistance.
Load resistance, then the output shouldn't change. Okay. So then the only parameter you need to specify is the trans impedance. Okay. And what about a current controlled voltage controlled current source? What is the input impedance of a voltage controlled current source?
Input impedance of the current control.
Of a voltage controlled current source. Voltage control means what? It is measuring a voltage and creating a current which is proportional to this voltage. So when you want to measure a voltage, what is the idea? You don't want to disturb the voltage that you are measuring, isn't it? So if you don't want to disturb the voltage that you are measuring, what comment can you make about the input resistance of your voltage controlled current source? Why?
Because we are measuring voltage, sir, so should not get disturbed by any change in this resistance, input resistance.
It should not get, come again?
It should not get affected by any change in input resistance.
What change in input resistance? Input resistance is not changing. Input resistance is there. What happens if there is input resistance?
Current will flow.
So basically, if the input resistance of the voltage controlled whatever source is not infinite, then it will draw some current which will disturb the voltage that is being monitored, right? So if you do, you don't want that to happen. Therefore, the voltage controlled current source must have a input resistance of infinity. And what about the output resistance of a voltage controlled current source? Abhishek, it's a current source, so the output resistance must be infinite. What about a current controlled current source? The input impedance must be 0. Why? All the current that you are trying to sense, so again, think of it as an ammeter. What is the internal resistance of an ammeter? Yeah. So basically, if the input resistance of an ammeter is not 0, then remember that ammeter is connected in series to measure a current. If it's got some finite resistance, a non-zero resistance, then it's going to perturb the current that's flowing, just like how a non-infinite resistance of a voltmeter is going to disturb the voltage that it is trying to measure. Does that make sense? Yes, no? Okay. So if you have a current controlled current source, therefore, what is the
Input impedance should be 0.
what about the output resistance? Output resistance of a current source is infinite. All right. So if you have basically these and the only so if you have a voltage controlled voltage source, I mean voltage controlled current source, what is the only parameter that you need to specify? The transconductance. And similarly, if you have a current controlled current source, what is the only parameter that you specify? The gain again. So, we will try to use again negative feedback to make either the gain or the transconductance or the transimpedance robust and independent of the properties of the transistor. All right. So, in the next class we will start looking at how to make an incremental voltage controlled voltage source in a way that the gain of the voltage controlled voltage source is robust with respect to parameters of the transistor. Okay. Thank you very much.